Okay, one or two of you need a little bit more practice in using these precisely to get the four SUVAT equations. The skills are all there, but I think we're just being a little bit sloppy on how we do the derivation. Like I said, it doesn't come up a lot, but you need to know it, and the better you know this, the more confident you'll be able to use it, and also understand the strengths and weaknesses of them. Now you should know, of course, when we begin this, the principles behind this. So we've got a velocity time graph, and some of the main points are that the gradient tells us the acceleration, and the area underneath the line tells us the actual displacement of the moving object. Now, we begin with the equation for this graph. We know that the initial velocity u is here, that's where we begin. Be very careful you don't say the initial is here at the origin, because sometimes it is, sometimes it isn't. It's wherever the y-intercept is, or if there is no y-intercept, or the y-intercept is 0, then it is at the origin. Anyway, that's our initial velocity, and here is our final velocity v. What we also have is that area underneath it is s. We'll come to that later on. So what we can see here is the final y-axis value, we can call that y, is equal to the gradient multiplied by the x-axis value plus the y-intercept, so mx plus c, and we substitute those. Well, that y is the v, the final velocity is acceleration multiplied by time, because that's our x-axis value, plus the initial velocity. Conventionally it's written as v equals u plus at, just because the initial velocity comes at the beginning, it's initial. So that's the first of our SUVAT equations, and it's a fairly simple derivation. Let's move on then to the next of them. So what we can also do is we can look at these two values and average them out in order to get the average velocity for this whole time. So what we do is we go halfway. We don't even have to do this in the diagram, but this is a way of doing it visually. So go halfway and we see that we can take the average of those two, and this should fit nicely in there. So to get that average speed, so I'm going to say average velocity v sub average is equal to v plus u divided by 2. Now, of course, then what we can do is take in this velocity, we can get the actual displacement, because we know that displacement s is equal to velocity multiplied by time. So then all we do, s is equal to, we'll write it this way because this is the kind of way they do it, half v plus u t. Very nice. Okay, and that is the second of our SUVAT equations. Right, box around that. The third one, this one is when you don't have to remember. They will always give it to you in the paper, but you're expected to use it quite a lot. Okay, this turns up a lot, and it's also for distance. We ignore this line here. We're going to focus on this rectangle and this triangle. So we can see very easily that the dimensions of this rectangle is ut, but of course we have to add in this triangle here. And so to get the area of this triangle, what we can see very nicely is that the height of the triangle is v minus u, so we'll say that. But of course to get that area we have to divide by 2 and also multiply by t. Okay, now let's just write this differently just to make it neater and tidier. So s equals ut plus 1/2 v minus ut. Still in shot. Okay, and we can tidy this up even more, because let's look back to this equation here. If we rearrange this, what we get is v minus u equals at. So what we can then do is we see the v minus u term turns up there and there, so we can substitute in at. So we substitute at in there, so it becomes s equals ut plus half att, or finally s equals ut plus 1/2 at squared. Now to come back to the point of all this, what we've got here is an equation where we can figure out the actual distance traveled if we don't know the acceleration. Here what we've got is something which lets us relate distance if, for example, we don't know the final velocity. Or, if we don't know anything about the final velocity and we know all these other things, we can find time, for example. Okay. Nice thing about this is if your initial velocity is 0, then this just disappears. And so s is just equal to half at squared. Let's look at our final one. And again, the easiest way to derive them, the most consistent way to derive them, is always beginning with s. So s is equal to v plus u divided by 2 multiplied by t. So I'm just taking this equation and breaking it apart a little bit. All right. What we can also do is this t term, again, coming back to the equation of the line, we can rewrite that as t equals v minus u divided by a. And so we're going to substitute this in all the way down here. So this becomes s equals v plus u divided by 2 multiplied by v minus u divided by a. These are being multiplied, so we can rearrange this to tidy up a little bit. So what we then get is 2sa or 2as, that's the way they normally write it. So what we do is we multiply this in, equals v plus u times v minus u. Expanded brackets, what we get is v squared plus uv minus uv minus u squared. Tidy that up, and what we found, so what happens is the uv's, they cancel. What we get is v squared minus u squared equals 2as. And you see what we have here is an equation which helps us relate all those things together if we don't know time. So to sum it up, what we've got is 4 very nice, very, very useful equations, which, okay, so I say very, very useful. They have a limited use because they only apply when there is uniform non-zero acceleration. If, for example, we had no acceleration happening, using this equation would imply that it traveled no distance, but it might have. Okay, although no, it actually would work fine because your ut term still gives you the distance. Anyway, uniform non-zero acceleration. So what we have is 4 equations: v equals u plus at, s displacement is equal to half v plus u t. S equals ut plus a half at squared. And finally, v squared minus u squared equals 2as. Some people write it as v squared equals u squared plus 2as, whichever, doesn't matter. Okay, there you go. That's the derivation.